Good evening, everyone.
Good evening, ma'am.
Yeah.
Good evening, ma'am.
Okay, so today we will be starting with metal clusters. So this metal clusters has been divided into two parts in your syllabus. So in the first section of the metal clusters, we'll be dealing with carboranes, metalloboranes, and metallocarboranes. And in the second part of today's class, we'll be dealing with the second part of the metal clusters. So starting from today, so we'll first begin with the metal clusters concerning to different types of boranes. So that is, we will be dealing with boron chemistry. So now metal clusters, generally they have these, in this unit it is particularly based on the boron based cluster chemistry. So the first thing, that is what a metal cluster means, is that the clusters that is formed between the metals, and in most of the cases the transition metals, they have been found to form metal clusters, and particularly the transition metals of the second or third series. So it is the first series transition metals, they are not very fond of, they are not very favorable the condition for forming of metal clusters, whereas metal clusters are usually found in the series for the second and third series of transition elements. Like for example, we have rhenium Cl8. It contains a cluster of Re single bond, and rhenium, it is not found in the first transition series. So now the first thing that the question that arises is, why the elements of the transition elements, they form metal clusters? And this is particularly because of the enthalpy of the atomization of the transition elements. Plus we also know that the transition elements, they have these vacant d orbitals. So when we consider the second and third row transition series, we know that the effective nuclear charge, it increases as the size of the d orbital, and as the z it increases, then the size of the d orbital, it decreases. Now when the nuclear charge, this effective nuclear charge is high, so then there is an effective overlap and the decrease in the size of these d orbitals. This favors cluster formation. So like for example, for the first row transition metals, which usually shows transition states of plus 2 and plus 3, they do not show this favorable overlap, and therefore they do not favor this cluster formation. So, thus, in this context, these binary boron hydrogen compounds, which we call it as borons, they have gained very prominence, and this is because, and they have grown into a very wide class of compounds. They are extensively studied, both because of their unique structure and properties, and also in their very unique applications, both in medical applications and also in environmental applications. And particularly, so we'll start with some the boranes. So here the boron hydrogen compounds, they are commonly called as the boranes, and we know that a series of boranes are formed. So the lower boranes like B2H6, which is commonly called as diborane, B4H10, pentaborane, hexaborane, these are the lower boranes. They are mostly, they exist in the form of either volatile liquids or gases. And what happens is, they are, when they come in contact with air, they are highly explosive in nature. So these lower boranes, they are stored in airtight containers, and in figure 8.1 you can see some of the structure of these lower boranes. Now almost 35 neutral binary boranes, they have been known, and they had these neutral binary boranes, they have been listed in table 8.1 along with some of their physical properties, such as their melting point, boiling points, and their thermal stability, and there are some physical properties here it has been listed. So this table, it shows, you can see the starting from diborane to dodecaborane to all those, and it has been listed here. So, and here some the stable and the isolated boranes, they have been indicated, so which we can isolate, and these are here listed in table 8.1. So now coming to the some of the preparation methods of boranes. So one of the most widely used method for synthesis of polyboranes is the pyrolysis of diborane. So pyrolysis, as we know, it is carried out in an inert atmosphere, and the reaction temperature is always mostly kept above 400 degrees centigrade. So the pyrolysis of B2H6, it has been mostly used for the synthesis of different class of polyboranes. So polyboranes are those boranes which contain the boron number is greater than 3 always. So here in organic, mostly in organic synthesis, the diboranes here, they are obtained. We organic compounds like these, the equations in 8.1 and 8.2, they show the preparation method of NaBH4, and we know this NaBH4 and LiBH4, these are good reducing agents. So with the use of these reducing agents, we can obtain the series of boranes, diborane. Here in equation 8.3 to 5, it indicates the use of lithium aluminum hydride and sodium borohydride on BF3 or BCl3 to form corresponding diborane. These are the common methods listed for the preparation of B2H6. Now, in the laboratory, the best method for preparation is the hydride abstraction from BH4 minus ion, here as it is shown in equation 8.6. Now, with the help of this hydride abstraction, this is mostly done in CH2Cl2, that is DCM, dichloromethane. So, and the hydride is abstracted. With this process, very pure higher boranes, they are obtained in volatile forms, and they also form larger anions. Like for example, the treatment of B3H8 minus salts with boron trihalides, they give the best available synthesis of tetraborane, that is B10. So as here it is represented in equation 8.7, if we treat B3H8 minus with a boron trihalide, so X minus, this X, it might be boron FbF3 or BCl3 or BBr3, we can obtain a higher borane, that is B4H10. So here it is shown in figure equation 8.7. Similarly, with the use of B4H9 minus anion, pentaborane, it can be synthesized. So some of the equations here, it is represented in equation 8.8. Hexaborane, here it is prepared by this method, that is indicated in equation 8.9. So some of the common examples of preparation of different types of borane, here B10H14, they have been you prepared from two methods. By one is by the hydride abstraction, and other is the metal promoted fusion using FeCl2. So Then coming to the characterization of higher boranes other than B10H14, all except this B11H15, it contains the 10 two or more clusters. So like for examples, here it is shown in figure, if we look into figure 8.2 here, in 8.2 some of the polyhedral boranes they have been shown here. Now the formation of B2 B12H6, it is the only known neutral dodecaborane. It is promoted through the oxidative fusion of hexaborane, and it is represented in figure in equation 8.16. Now coming to the preparation of polyhedral borane, so here the polyhedral borane, it indicates that the n it ranges from 6 to 12, so they are deltahedral clusters. A deltahedron, it means that it is a polyhedron and where it has only the triangular equilateral triangular faces, so that structure it indicates a deltahedron. So here it is, as here it is shown in figure 8.2. So these are the structures of polyhedral BnH2n minus dianions, and different polyhedrons here have been shown in figures A to G. So compared to neutral boranes, these anions they are actually more stable. So in general, we can say that these dianions they are more stable than the neutral diboranes that we talk about. So here another striking difference of these borane anions from neutral boranes is that the B2, these dianions, they are highly soluble in water and they form stable solutions. So most of these anions, they are formed by condensing small borane fragments. So these anions are prepared from mostly from the borane fragments. Like if we take diborane B2H6 and the reducing agent is NaBH4, and we take EP3N, that is tetraethylamine, and the temperature is maintained from 100 to 100 degrees and 80 degrees centigrade, then this product is formed, which forms the corresponding anion, dianion. So here in equation 8 8.8 8.19, some of the other preparation methods of dianion borane dianion has been shown here. Now coming to the various structures and bondings in borane. So we know here the structure, particularly for indicating the structure in boranes, we have three prefixes. That is, the most common prefixes are the closo, the nido, and the arachno. So here when we will talk about, we are talking about the structure of the borane dianions. So when we talk about the closo, it indicates a closed polyhedron. The geometry is closed in nature. Whereas when we talk about neutral boranes, they have open structures. Now here, when we look into figure 8.3a, so here, if we look into the vertex of this polyhedron, all the six vertices are occupied. So this indicates a closed structure. Now, when we remove one vertex from this figure, here six vertices, they are indicated by the bold dots. So if we remove one vertex from this figure, then we obtain a nido structure. Here only five vertices are present, so that is called as a nido structure. A nido in Latin, it means a nest type. So here the nido structure with five vertices is shown here. Now further, if you remove another one vertex from the nido structure, then we are left with only four vertices. So here, and it is called as a arachno structure. So starting with closo, that is a closed polyhedron. The removal of one vertex from the closo structure, it forms a nido, and the removal of one or more vertices from the closo structure, it forms the arachno. So in the three figures, the boron framework, it has been showed here in figure 8.3. The A, it indicates the closo, in B it has shown the nido, and in C it has shown the arachno. So these are the some of the most common boron frameworks that we talk in boron chemistry. Now, so here the closo, nido, and arachno for B5H9, here they have it has been shown in these figures. So now when we look into this is the actual, when we look into the structure of B2H6, that is shown in figure 8.3. Now B2H6 is a very common diborane, and when we look into the actual structure that is represented in figure 8.4, so we see that there are four BH terminal bonds. These are the four here. We see this is 1, 2, and 3, 4. These are called as the 4BH terminal bonds. And we see a 2 3 center BHP bond. These are the 3 center 2HP bonds. This the structure of diborane is typical in nature because this the 3 center BHP bonds. These are commonly called as banana bonds, and this is how. So the structural representation of B2H6, here it indicates 4 BH. Here it indicates 4 BH terminal bonds and 3 centered BHP bonds. So here each boron atom, it has 4 valence electrons, those are sp3 hybridized, and that can accommodate 12 valence electrons. So now this structure of particularly of diborane, it is analogous to ethylene, that is C2H4, and it is also isoelectronic with ethylene. And this BHP bridges, they can be regarded as protonated double bonds. So however, in both B2H6 there is no, and C2H4 there is no deficiency of electrons, and all the bonding orbitals are filled. So now when we apply the valence bond approach to all the neutral boranes that are present here, we can find BH bonds and 3 centered bonds. So like here in this application to B6H10, that is shown here in this figure 8.5a, the application of this 3 centered bond has been shown for a hexaborane, that is B6H10. So this is a pentagonal pyramidal geometric structure, and here the 3 centered bonds plus 2 centered terminal bonds here has been shown in this structure. So likewise, we can apply this valence bond approach to determine the structure of neutral boranes. Now coming to Wade's rules. So this Wade's rule, it is initially they were called as the PSEPT. So this is polyhedral skeletal electron pair theory. Since it was developed by Wade and Mingos, it is called as the Wade's rule. So here, actually based on this rule, we can predict the structure of the diborane compound. So it follows some certain rules. So the first rule, it says that the polyhedral clusters, they are assemblies of building blocks that contain the BH unit. Since we are dealing with BH, so we will be just focusing on the BH unit. The cluster geometry is found out first we need to find out the total number of skeletal bonding pairs from all of the individual block units. So that is why, so it is always important we find out the total number of the skeletal bonding pairs that is present in the block units. So like for this we have to actually consider an example, then it will be more easier. Now, so if we for and the most important thing that needs to be remembered here is that the contribution of a BH unit is always 2. So and so first, once we find out this, the total number of skeletal bonding pairs, then applying this rule, we can say that the if the number of the vertices is found out to be n, then the n plus 1 structure is called as closo. If the n plus 2, it is nido, n plus 3 indicates arachno, and n plus 4 pairs, it indicates hypo. So first we will take this, consider an example. Let us consider the case of B5H9. So where for the B5H9 there are 5 BH units and 4 bridging hydrogen atoms. So this is the preliminary thing that needs to be considered here. Now for each BH unit, the number of contribution for electrons is 2. Since 5 BH units are present here, so total number of electrons is 10. And since we have 4 bridging hydrogen atoms here, so they contribute 1 electron each. So in total, we can say 10 plus 4 is equal to 14 electrons. Here it is present in the B5H9, and 14 electrons, it indicates a total of 7 pairs. So now we have to put this value in terms of n. So here the BH unit, the number of BH unit, it corresponds to n. So here n is equal to 5, but we found out that the total pairs of electron pairs is 7. So 7 indicates n plus 2 electron pair. Now we will correlate it, this n plus 2 with our Wade's rules, and we know that if n plus 2 electron pairs are present, then it is a nido structure. So this is how we predict the geometry of different types of boranes. Now, similarly, here in another example, the B4, the B10H10 of the geometry of B10H10, it has been predicted using this PSCPT approach. Now, although this approach is particularly applicable to boron clusters, this has also been used for other carboranes, metalloboranes, and other metallocarbon carboranes particularly. Now, here we can see the complete structural relationship between closo, nido, and arachno species. It has been depicted in figure 8.6. So here the diagonal lines that is present in figure 8.6, they connecting the species, they represent the hypothetical transformations, that is the removal of the boron vertices moving from left to right, and it shows the interconversions occurring in them. So this is how the structure of nido, arachno, they have been between A and B, it has been shown. So now, if so as to confirm, we need to find out the molecule. If we ever need to find out the molecular orbitals of delta hedra means it is the plural of a delta hadron. We may simply say that for a regular delta hadron that has n vertices, then the number of bonding molecular orbitals is given by n plus 1. And the electron capacity of these bonding molecular orbitals is n plus 2. So based on this approach, we have an important formula here, that if the total formula is 2n plus 2, then it is a closure structure. 2n plus 4, it indicates a nido structure, and 2n plus 6, it indicates a arachno structure. Here in this figure number 8.7, the structural relationships of the closo, nido, and arachno of the boranes, they have been shown here, and the total representation here, it is shown how we can correlate the structure and their geometry. Now with this, again we'll start with coming to carboranes. So carboranes are also, they are a class of boron clusters with one or more carbon atoms. It is present in the borane framework. So carboranes, they are particularly what we call it as caged metals. So in each cage, the two skeletal carbon atoms, they are found for the synthetic species. Like some of the isomers of planar heterocycles have carborane type geometries. Now, one very common carborane is this FbC4H4B. It has a classical planar structure. So these are, when we talk about particularly carboranes, they are considered as non-classical molecules. Now coming to closocarboranes. So here in table 8.2, some of the species of closocarboranes that have been isolated and characterized, they have been shown here, and their cage geometry is also so represented here. So now when we look into the n vertex of the carboranes, they show similar cage geometry as that is shown by its corresponding BnH2n dianion. So here in general, this is by using the PSCPT rules, that is the Wade's rules, where we always know that BH unit, it contributes 2 electrons, but particularly when we talk of carboranes, the CH unit, it contributes 3 electrons. So when the total count is 2n plus 1, this suggests closo structures. So this is how the geometry is predicted in carbonates, and particularly we need to remember that the CH unit, it contributes 3 electrons rather than BH units which contribute 2 electrons. So here in figure 8.8, the structure of various types of closocarboranes, they have been shown. Some of the known closocarboranes, they have been shown. Now the coming to the here, the preparation of these carborane cages, particularly they have applications in the field of particularly plastics, elastomers, and mostly they have been found in, also they are used in medical applications for treating brain tumors. Now another series of closocarboranes which is isoelectronic with BnH2n di minus, they are the C2BN-2HN compounds. So there are various routes for the preparation of such closocarbonates, and one of the examples here, it is shown in equation 8.21. Now coming to the polyhedral rearrangements in carbonates. So here intramolecular rearrangement are possible on the cage skeleton, and this is a very common feature for closocarbonates and other boron clusters. So this mostly occurs due to thermal rearrangement. So thermal means, so when heat is applied, rearrangement and isomerization takes place. So these isomers, which have maximum CC separation, they are capable of separating and and separating the positive carbon cage nucleus. So the following, if you look into the following example, like octahedral 1,2 C2B4H6, it converts to 1,6 isomer at 250 degrees centigrade. So we see the temperature, that is thermal isomerization, it leads, it is this rearrangement is could be attributed to the thermal isomerization, that is temperature, high temperature is needed. So similar example is icosahedral 1,2 C2B10H12, that is orthocarborane. It undergoes rearrangement above 425 degrees centigrade to form the 1,7 isomer, and also further at higher temperature it goes decomposes to form the 1,12 isomer. So we see that the polyhedral rearrangement occurs as a function of the temperature that is applied to it. Now the mechanism of this rearrangement, it involves many pathways. So however, the exact mechanism is not yet established, but the diamond square diamond, that is the DSD processes here, that is shown in figure 8.9, it is widely accepted for the this intramolecular rearrangements. Then coming to nido and arachno carborants. So the open cage geometry in carborants, they are much diversified as compared to the closed structures, that is to the closure series. So here in table 1.3, the open cage carborants, they have been listed and some of the examples have been given. So the isoelectronic and isostructural analog of B5H9, that is pentaborane, is nido 1,2 C2B3H7. So this 1,2 C2B3H7, it is unstable in nature and it polymerizes to nido 2,3 C2B4H8. So this is the first carborane that is reported from thermal or base promoted reactions of acetylene with B5H9. So various other such derivatives, they have been discovered, and other closer and other nido and arachnocarborants, they have been discovered. The reactive open cage carborants and their deprotonated anions, they are often, however, they are more accessible and they are more prone to suitables. So here an interesting class of sandwich ligands, they have been formed when we look into figure 8.10. So most common ones, they have been prepared by the deprotonation of neutral carborants. So here when metal ions, they coordinate with the 12 vertex nidodiene ions, then 13 and 14 vertex metallocarbons are formed. So here we can see in figure 8.10 a various nido selection of nido and arachno structure carborants with some of their substituted derivatives, they have been shown. Now in equation 8.22, it shows here this equation, it shows the preparation of C4B4 cage by inducing an alkyne into E2 into ethyl C2 before H6. The metal promoted oxidative fusion. This leads to formation of sandwich complexes. So this sort of reaction is promoted by transition metals and it is important in the synthesis of nido and arachno carborants. So in equation 8.23 and 8.24, the synthetic approach for the tetracarbon carborants, arachno and the nido structures have been shown here. Now, metallocarbons and metalloboranes and metallocarboranes. So, for the synthesis of nidocarboranes, then it was why during the synthesis of nidocarboranes, it was found that the C2B3 open phase, it was similar to that of the C5H5 minus ion. So, which suggested that there is the formation of sandwich complexes which is similar to that of metallocenes. So hence further experiments were conducted and a new class of compound called as metalloboranes, they were first discovered. So metalloboranes, these are boron cages that contain one or more metal atoms, but there are no carbon atoms in their skeleton. So here in figure 8.11 and 12, as here it is shown, we can see a number of metalloborins, the examples of number of metalloborins, they have, it is been shown here in this figure. And we can see there are the number of, they have here small vertex of 4 to 5 and small cages, also multi cages here they have been shown. So most of them, the particularly the examples that have been shown here, these structures they have been isolated. However, sometimes the reaction, they are the reaction of the boron hydrides with the controlling the reaction parameters is sometimes very difficult. So these structures are very difficult to obtain. So here, if one of the metal atom it gets into the cage, then even sometimes trimetallic isomers are also formed, and this particularly happens when the boron substrates, that is the smaller lower boron substrates, they are very susceptible towards the metal reagents that have been taken. So for example, some this these complexes of this type CP4, CO4, B2H4 and metal boride clusters, they have been obtained differently, and they are like they have been formed reaction of metal clusters with monoboron reagents, and they have been utilized forming larger clusters. So now, since we have studied Wade's rules, we can also apply these Wade's rules in the metalloborins. So, and we can actually predict their geometry similarly from the Wade's rule that we have studied. So this also follows certain, particularly two rules it follows, that each metal atom occupying a vertex in the cage, it utilizes exactly three orbitals for binding to its neighbors in the framework. So in case when main group elements are used, then mostly four valence orbitals are found, only one orbital is left behind. But when transition metals are used, they have nine valence orbital, out of which three are for cage binding, and the six orbitals they are left for other binding to other groups or for non-bonding. So when we talk of a transition metal, out of the nine valence orbitals, we should always remember that three are only utilized for your cage binding, and others they remain for the binding to other atoms. So after this, once we find out this, the calculation is done on the basis of the skeletal electron contribution. That is, we find out the contribution of the electron pairs, we calculate the total number of contribution the electron makes to the contribution to the skeleton. And here some an example of the electronic configuration here with different unit, it has been shown in figure 8.13. So here the FeCO3 fragment, it has been found to be a 2 electron donor, whereas the CpNi it supplies 3 electrons. So certain these rules and certain exceptions they need to be followed while considering these rules. So now this PSEPT, it has been found to be obeyed by metalloborins in most of the cases. Like the closo species, they adopting the polyhedral structures, they are analogous to particularly BN, HN, dianion analogs, and the open cage complexes, they have the geometries of their neutral boron counterparts. So this, in general, these two rules depict the geometry of the metalloborins. However, when there are certain exceptions. For examples, the CP4, M4, B4, H4 clusters, where this M it might be your nickel or cobalt, then 16 and 20 skeletal electrons are present, but they adopt closo 8 vertex polyhedral structures. So this is one exception to this rule, and this is what we call as a slip distortion, and this is called as a closo to nido cage transformation, and this is quite common for such type of complexes. Now, metallocarborins, they are compounds which have both metal and carbon atoms in their cage skeleton. Then, while synthesizing metallocarborins at low temperature, by inserting metals into the carborane anions in solution, the reaction it is more controlled, and it is particular than that the synthesis of metalloborins. So, some of the reactions it has been shown here in the that are much used in synthesis, it has been shown from equation 8.25 to 8.27. Now particularly here in figure 8.14, the structures, different structures of metallocarborins they have been shown. So these metallocarborins also they follow the Wade's rule, that is the PSEPT rules. Even though most of the metallocarborins they have two carbon atoms per cage, other carbon 1, 3, 4 carbon metallocarbons have also been known, and mostly transition metals, lanthanoids, main group elements, they form such complexes. And it has been also been known that more than one metal they can occupy in the same cage framework. If you look into this figure A, this has only iron, whereas here in in the figure J, we can see the presence of two iron. So it is known that more than one metal they can occupy the same gauge framework. So that is also possible. Now, since the controlling the synthesis reactions of metallocarbonates, it is easier as compared to those in metalloboranes. So these metallocarbonates, they have been first studied in extensive details, and their structures are also much more elaborated than those of the metalloboranes. The closometallocarbonates, they show different the reactions of carbonates, such as the substitution, cage expansion, degradation, electrophilic halogenation, while the nidometallocarbonates, they undergo bridge deprotonation similarly as their boron counterparts. However, among all these reactions, the most extensively studied chemistry of metallocarbonates, it involves the metal centers. Despite their susceptibility to a wide range of reactions, metallocarbonates, they particularly dealing with their metal chemistry, they have been studied the most. So here in figure 8.14i, so what has been done is a typical catalytic reaction of the species. It has been shown here that has been particularly used as catalyst for olefin polymerization. So in these applications, metallocarbonate species, they resemble their metallocene counterparts. Figure 8.5, it shows the golden bridge tungsten carbene complex that is representative of a very large diverse family of the metallocarbonate, and we can see MC2B10 cage units. So this is a very large family, and this is a gold bridge tungsten carbene complex. So that has been synthesized, and this molecule is quite large, incorporating MC2B10 or MC2B9 units, where M here it indicates the metal that is used. So heteroboranes, these are boron cages containing one or more non-metal atoms in the skeletal framework. So these are called as some heterocarboranes. So they include most of the elements of the group 13, 14, 15 and 16. However, in most of the cases, group 15 elements, they have been widely used. Particularly group 15 elements such as N, P and arsenic, they are isoelectronic with CH, and they are 3 electron donors to the cage. So icosahedral species such as PCB10H10 and AS2B10H10, these are all isoelectronic with C10B10H12. So they have been found, and mostly they have been easily synthesized. So heterometalloboranes and heterometallocarboranes, they are obtained when a transition metal atoms, they are introduced in their cage framework. And here in equation 8.28, some of the reactions, the preparation has been shown. Particularly here in 8.28, such type of complexes, this is called as the tetradecker sandwich complexes. Multi-decker sandwich complexes is their general term, but since when we look into 8.28, this includes sandwiched complexes, and it is a four layered, so it is called as a tetradecker sandwich complexes. In particularly in such type of sandwich complexes, the carborane or the organoborane, it binds to the metal atoms here as it's shown. This is the carborane or the metal atom. They binds to the M, that is the metal atom, on both sides of the plane, on both sides of the on the both the axis of the ring. So that is why they are called as sandwiches, and depending upon the number of the layers, they are termed as tetradecker, tridecker and multidecker. So that is why they are called as such type of complexes, and here it is shown in equation 8.28. So with this, we finish the first part of metal clusters. Now coming to the second part of the metal clusters. In this second part of the metal clusters, we will be particularly dealing with MM bonds, that is the metal-metal multiple bonds. Now, in metal clusters, the bond between the metals and the metal, that is the mm bond, it is not always single bond. So it might be double bond, it might be triple, or even it might be quadruple bond. So particularly in transition elements, since they have orbitals as valence shell electronic configuration, the presence of these vacant d orbitals, it enables and it eases the formation of such metal-metal bonds. Now metal clusters in general, that is the mm bonds, they show three major types of bonding. So one is the covalent bond, one is the dative bond, and other is the weak metal-metal symmetry interactions that we have that discussed. So in general, we can say that the metal-metal clusters, they comprise of three types of bonding in between them. So first, starting with the covalent bonding. So this is the most common type of metal-metal bond. So these bonds, they might be singular in single bond, or they might be quadruple bond. Here in figure 9.1, in the first case, we see this is a triple bond, that is MO triple bond. Whereas when we talk about the rhenium, here it is quadruple bond. So this bond, it is not always single or double, it might be quadruple. So here in table 9.1, the general criteria for cluster formation and the resulting mm bond, here it is determined. So when we look into table 9.1, D1, D1, if the electron count is D1 and D1 for both the metal-metal atom, and then a single bond is formed. So when it is D4, then quadruple bond is formed. Likewise, when we look into this table, we find that when D8 or D10 electronic configuration are present for the metal atoms, then what happens is the antibonding orbitals, it starts getting filled, and therefore the chances of the bond formation are very less. So and but this in particularly D8 case, here we see there is no bond. So because the antibonding orbital, it starts getting filling, and there is a chance of symmetry. So that is why bond formation decreases for D8 and D10. Then the next class of bonding in metal-metal clusters is the type of the dative bond. So dative bond, we know it is represented by a arrow, and a dative bond is mostly due to the donation of a lone pair of electron of one metal to the filled d orbitals of another metal, which coordinate by the dative bond. So this, in this example 9.2, this is a bimetallic nickel complex, and we can see here in this reaction, in this complex, nickel to nickel, the bonding between nickel to nickel, it's a dative bond. So here nickel has a D10 electronic configuration, whereas the nickel, this acceptor, it has a D8 configuration. The donor, the configuration of nickel donor is D10, whereas that of the acceptor is D8. That is why a dative bond is formed in this bimetallic nickel cluster. Then the third type of bonding in such complexes in metal-metal clusters is the weak metal-metal symmetry interaction. So we also have a metal-metal symmetry interactions, which they arise due to the symmetry interactions between the molecular orbitals of the metal. So this overlap, it is generally between the filled and empty metal-metal bonding or antibonding orbitals. So Harry Gray, he was the first scientist, and some of the common bimetallic or polymetallic D8 complexes, they exhibit these interactions both in solution and state solid phase. So here in figure 9.3, iridium tetrakis isocyanide complex, we find this metal metal bond. This is weak metal metal symmetry bond interaction. So this is the three type of major bonding that we find in metal clusters. Now coming to the principal types of compounds that having metal metal bonds. So we are now looking about the compounds that can have metal metal bonds and form the bulk of the transition metal chemistry. So first is edge sharing by octahedra. So here, as here we show in figure 9.5, this is the dd overlaps, and they also show a bioctahedral structure. Here in this figure it has been shown. So when there is a possibility, suppose for example, the molecules which show single sigma and double sigma to pi 2 bonds, this such type of cases arises. Suppose when two d4 metal atoms interact, both the delta type orbitals will be filled. So instead of a probable triple bond, double bond here it is present. So similarly, when we talk of a D3 system, the bond order might be 1 and it may not be 3. So this is also possible. So as the energies of the delta orbitals, they are very close. So what happens is the spin state equilibria, they are also observed. So here in figure 9.4a and b, some of the molecules that show sigma square and sigma square pi 2 square bonds have been shown, and this type, this in this presence of molecules, the delta type of orbitals will be filled, and which lead to this edge sharing by octahedra, and their orbital diagram here it is shown. So also in phase sharing bio-octahedra, there is also possibility of this metal-metal bond double bond formation. Like here in figure 9.6, we have W2Cl9 3 minus ion. So here it has a, if we look into this, it has a triple bond. So the general structure for the compounds where triple bonds, here it has been shown for niobium and tantalum complexes having double bonds, here they have been shown. So the complexes which has phase sharing octahedra, so we also, there is a metal double bond is possible. And then tetragonal prismatic structures, these group of compounds, they have bonds up to quadruple, and they have been studied in detail. Like common examples are Re2Cl8 minus and MO2Cl8 4 minus. These are the very common examples, and their structures here it has been shown in figure 9.8. The five possible overlaps of the d orbitals of the metal atoms, they have been shown. So here the overlap of the d orbitals on the two adjacent metals are possible in five ways, and here they have been shown. So the overlap occur in sigma, pi and delta overlaps, and their possible overlap has been shown here. So looking at this figure, we can see that the relative value of the sigma, pi and delta overlap, it decreases. It is first, here is sigma, then is the pi, and then is the delta. So five types of overlaps are possible between these d orbitals on metals like Re and Mo. So with the help of the molecular orbital theory, the overlap of the various orbitals formed, they can be studied, and then we can know the formation of the quadruple bond here as is shown in figure 9.8. However, we always need to see that the overlap of the d orbitals also can lead to other cases, like the each atom of the two metal atoms, it gives is dz square orbital for overlap, and they form sometimes a sigma bond. The dxz and dyz overlap of orbitals, they overlap to form two pi bonds. The two sigma, two delta bonds can also arise from the face-to-face overlap of dxy and dxz square. Sometimes the dxz and xz, x square minus y square, and dx square minus y square, they also overlap with other ligands to form this delta bond. So these are the certain conditions that also need to be considered if we need to check the possible overlaps of the d orbitals on metal atoms. So therefore, the electronic configuration on the metal quadruple bond, it is very different, and so this all these factors, it quite makes the conformation twisted, and therefore, so for particularly for quadruple bonds, eclipsed structure, they have been observed. Then coming to trigonal antiprismatic structure. So when in figure 9.10, the trigonal antiprismatic structure here it is shown. It is the major structural pattern that it has been shown here. The six ligands, as you can see, they approach here in the manner as it is depicted here. So molybdenum and tungsten generally form such type of complex compounds. Quadruple bonds in metal cluster, the delta orbital that is involved in the quadruple bond, is very weakly bonding, and the delta star orbital is also weakly antibonding, so their separation energy is very small, and the characteristic absorption band for these, it is for these quadruple bands is present in the visible region. So and this occurs due to the excitation of an electron from the singlet pi square pi 4 delta square ground state to the pi square to the sigma square pi 4 delta delta star excited state. Now these sort of transitions As a result of these sort of transitions from the delta square to delta delta star state, excited state, we do see the characteristic colors of the metal clusters, quadruple bonds of the metal clusters that contain quadruple bonds, like Re2Cl8 minus. It is a classic example and it has a royal blue color. Even MO2Cl2 minus, it is intense red coloration, or it is obtained in intense red color, and such other colors have been reported. Now, because the delta bond is very weak in nature, the gain or loss of the electron, it has a very slight effect on the strength of the bond. So here the strength of the metal metal bond in quadruple structures, they have been listed here, and we can see here the bond order, it changes from 3 to 3.5 to 4 when the delta star electrons are removed. So here in figure 9.11, it shows how one can delete or add one of the electrons to the delta and delta pi star and the delta star orbitals. And here the quantitative molecular diagram for dinuclear rhenium and molybdenum complexes. Here they have been shown. So in table 9.2, certain examples of diplatinum compounds which have bond order from 1 to 0. Here it has been shown here. The bond order ranges from 1 to 0.5 to 0, and here their configuration has been given. So with the change in configuration of delta to delta star, we can find out the bond order of such metal metal quadruple complexes. Now coming to metal atom cluster compounds and metal carbonyl type clusters. So types of metal metal cluster. So first is the dinuclear cluster. As the name indicates, it contains two metal atoms. So the Re2X82 minus, this is the rhenium-rhenium complex, is the first dinuclear complex that was discovered by F.A. Cotton. So the Re-Re bond distance was found to be 224 pm picometer, which did not match with the average reported value. So here the concept of quadruple bond between the two rhenium centers, it was proposed by Cotton. Here we know it has a staggered conformation and it forms a square antiprism structure. The metal metal bond cluster here are also formed in other complexes like tungsten or other complexes having the formula M2OR6. Then another is, after dinuclear we have trinuclear cluster. The best studied examples of trinuclear clusters are also the rhenium trihalides, ReCl3 and their derivatives. Here the each rhenium atom, it is bonded to other rhenium atoms by a directly metal metal bond, as here it is shown here. So Re3Cl9, this is a trinuclear cluster. Then tetranuclear cluster. Many tetranuclear carbonyl clusters are found, and some of the examples that exist in halides and oxides of tungsten and molybdenum, it has been shown here in figure 9.14. Then hexanuclear clusters, some these are very rarely known. First, a hexanuclear clusters of metal chlorides is the octahedron of the six metal atoms. They are surrounded by eight chloride ions. So here in figure 9.15, MO6Cl8 2 minus, this is a hexanuclear cluster and it has been shown here. And in figure 9.15b, this cluster is for tantalum. So this is a hexanuclear cluster. Then metal atom cluster compounds. So compounds like W2Cl93 minus, and which have a few metal metal bonds, they were discovered. However, the exact structure, it cannot be determined because X-ray crystallography was not present at that time. So structural determination of these compounds, they were rather difficult. Then came the concept of metal carbonyl cluster compounds. The metal atom cluster, they are mostly comprising of two classes. So here they are generally, what happens is, those with the metal atoms, they are formed in very low formal oxidation states, like mostly with the later transition groups like 7 to 10, and here they form C0 with the carbon monoxide is the ligand. And in the second case, metal atoms, they are in the somewhere of higher oxidation states and with the early transition elements. So and mostly the ligands they have been used are the halide sulfide or oxide. So then first of the metal atom cluster type complexes, we will talk about metal carbonyl clusters. So here metal carbonyl type clusters means, here like an example is a Mn2CO10. So Mn is present and carbonyl is present. So here Mn2CO10, it has been, and other such clusters have been formed. Even mixed metal clusters such as H2, Fe, Ru2, osmium 13 carbonyl, these are also present. So generally trinuclear clusters, they are triangular in nature. So typical examples, here it has been shown in figure 19.6a. So here the carbonyl groups, for particularly for figure 19.6a, this is of osmium. So osmium 3 carbonyl 12 cluster here is given. The closed cell configuration when each metal has an 18 electron in it is shown here. And similarly, when we look into figure B, 9.16b, osmium 12 carbonyl, we found that there are 46 electrons, and here it the unequal, the length of the edges of the triangle, that they are not equal length, they are of different length. So these two possibilities, the representation for both OS3CO12, it has been done, and the among this, the formal 18 electron configuration can be only attained if there is only one OS, double bond OS. So more derivatives, they can be obtained from these structures. Three important points that need to be remembered, that if we replace one or two CO ligands from this structure, then more reactive species are generated. So some of the chemistry of the osmium system, here it is shown in scheme 9.1. Like here, it from this OS3CO12, one OS has been removed and other groups have been attached to it. So it has been found that they become more reactive and they are good synthetic reagents. So here in scheme 9.1, we do see some of the reactions of osmium forming newer structures. In equation 9.1, here it is represented the reaction of OS3CO12 with hydrogen at 125 degrees centigrade, where which leads to displacement of two carbonyl groups, unsaturated and reactive H2OS CO10. Here it is formed. So when we react this, we find a product. This is a very important reaction, and unsaturated and reactive, this is very reactive in nature. Now when we, in scheme 9.2, some of the reactions of osmium 3CO12 and its Fe analogous, here they have been collated. Here it is shown in scheme 9.2. Then the methyl compound that remains in equilibrium with methylene breached isomer, and it has been isolated from this solution and they have been characterized. So heteronuclear 4 atom clusters have been shown in figure 9.17. So also 4 atom clusters, they exist in butterfly form and in planar form. This is shown here in figure 19.8a, 19.8b. A represents the butterfly structure and B shows the planar structure for 4 atom clusters. Now anionic and hydrido clusters, if we count the total electrons, we see that one CO can be replaced by two hydrogen atoms, one H and one negative atom, and or two negative charges. So protonation and deprotonation reaction takes place easily, and there is no change in the cluster structure also. So exceptions do occur, and here if we look into such type of reactions, osmium cluster for the protonation and deprotonation reactions, and there is also the change in the structure that we can found here. So large clusters, they are relatively strong polyacids in nature. So sometimes with X-ray diffraction, there has been found to be certain results. So these are the structure of some of the osmium polyhedrals that has been shown. Now the particularly the existence of larger carbonyl clusters, it involves it of the existence of larger carbonyl clusters also makes us wonder that how are they possible in to remain in such larger form. So the four major types of structure found are closed polyhedra that is called as a octahedron, the trigonal bipyramidal structure, trigonally distorted octahedron, and a cube. Closed packed arrays are also formed, stacked triangular arrays are formed, and they are also formed in racks. Now coming to synthesis of metal clusters. So however, not much mechanism has been studied for this. So one easy vacuum pyrolysis here has been shown for the preparation of OS3 CO12 uh, for OS3 CO12 cluster. So in equation 9.2, a carbido cluster may have been prepared and it has been represented in these equations. So also in very using milder reactions, other clusters can be synthesized. In scheme 9.3, larger clusters of osmium formation, it has been depicted in scheme 9.3. So here heteronuclear products shown in equation 9.4 and 9.3 and 9.4, these are also prepared by the reaction between carbon metallides and neutral carbonyls. Also, simple halides, they react with carbonyl anions as shown in equation 9.5 and 9.6 to produce other metal clusters. The structure of gold nickel cluster, it has been like tetrahedral symmetry with a metal core, and it has been similar to that of a AU6 octahedron, and here it is represented in figure 9.21. This is AU-Ni cluster representing the all the fragments and the faces of the AU6 octahedron. So this is a super large cluster. Even other super large clusters of the anion, they have been found and they have also been isolated. So the presence of the heteroatoms within or the metal clusters, they indicate and they often modify the structure and the properties of the resulting clusters. I will just take a break for 10 minutes and then resume with the clusters. So now coming to the counting of electrons and the capping rule. So the counting of electrons here in clusters, they also follow the weights rules that we know, but here the some of the rules have been modified. So here we know that for the clusters the faces are called as deltahedral because they all resembles the equilateral faces of the equilateral triangles, and hence also so we need to consider the following rules while calculating the electronic configuration and for determining the geometry. So the 2n plus 2 rule for closoboranes is also it is applied to closo metal clusters such as OS6 18 CO2 minus. The 2n plus 4 and 2n plus 6 electrons would count. It is also applicable for clusters with nido and arachno structures. The hydrogen atoms, they are assumed to contribute one electron each, and the interstitial carbon atoms they contribute four electrons. So while the first number of calculation of the number of the skeletal electron pair is done, and this particularly other parameters, that is the TEC, it is first obtained, the total electron count is obtained. For the calculation of the TEC, the following contributions are taken into consideration. First is we need to know the number of the valence electrons on each metal atom, then two electrons from each carbonyl group, one electron for each negative charge, and then the total number of valence electrons that is present on the hetero or the interstitial atom. So for to explain all this, let us consider an example. So we'll take a easy example, that is RH6 CO16. So the total number of electron count for this electron is, since here RH is 6, so this is 6 into 9 plus here we have 16 CO. So 16 CO, it indicates 2 into 16. So the total electron count here is 86. The number of skeletal pairs is given of half of TEC minus the 6 into 12 that it has been done here, and it is found to be 7. So the number, the vertices here it is present, the is 6, and the structural and the is that it is a closure structure. So similarly, based on this type of calculation we can predict the structure of the cluster in terms of closo, nido and arachno. So now other cases, suppose we have a MCO bond, the total electron count is varied from the previous rule. So a closo polyhedral cluster of n vertices, the result would be 12n plus 2n plus 1. So these are some of the predictions that we need to do, so that this is overall it can be written as for closo it is, here in all the cases the n here it represents the number of the vertices. So the 12n plus 2n plus 1, for nido it is 12n minus 1 plus 2n plus 1, and for arachno it is 12n minus 2 plus 2n plus 1. So when we want to predict the structure, we calculate the TEC and further we subtract 12 metal from the skeletal pairs. So once we get the number of skeletal pairs, then most likely we can find out the structure of this. So here for example it has been described here. So in table 9.3, so various structures they have been shown. So now coming to the capping rule. So capping rule, it is important for calculating, it is particularly for predicting the structure. Now we know that many carbonyl type clusters they consist of a central polyhedron to which more or one or more metal atoms are added by placement over the equilateral triangle face. Now such metal atoms that are added to the face they are called as capping atoms. So the electron counting rules they can also be it is applied here, and an example here it is shown for the calculation of OS7 CO21. So the total electron count for this cluster is 7 into 8 plus 21 into 2 coming from the carbonyl. This is 98. Then we subtract this 7 into, we subtract 84 from 98, and further dividing it by 2 we get S is equal to 7. So the prediction is that it is a, the n here it is 6, as we got S is equal to 7. So the n, that is the number of vertex, is 6. So that is closo octahedral and it is capped on one face, which is correct. So this is the representation of what we have got, and this is how we can calculate. So here in 9.4, the TEC, the number of electron pairs and the structures have been shown for certain various types of clusters. So there are certain limitations and exceptions to this capping rule. The Basically, the transition metal clusters, they have high nuclearity. They are formed by condensation of small clusters like tetrahedron, octahedron, and trigonal prism. So with this, basically, the limitations, the rules that have been taken into consideration are that the number of atoms and number of electrons on the individual polyhedron should be known. And once condensation has occurred, we always need to know the in case of TEC, we write here PEC, that indicates the polyhedron electric count, and it is also the same that we used in Wade's rules. So we can apply this rule and an inert gas formalism that has been maintained here. Here in table 9.5, the electron count of such cluster compounds have been shown. So based on the above rules, the possible, we can actually predict the different geometries or the possible structures of clusters, and some of the examples here, they have been shown in figure 9.239 and 9.24. So with this, these are some of the questions that are related to the metal clusters, and with this, the unit of clusters, the block 2, that consists of the organometallic compounds, metal carbonyls, metal pi complexes, and metal clusters, is finished. Then we'll start with block 3, which is unit 3, and this unit particularly deals with crystal field splitting theory and its applications. So first we'll understand what is CFSC. The first we'll go for CFT, that is the crystal field splitting. So firstly, it is actually based on two main assumptions. The crystal field theory is, first it says that the ligands, they are considered as point negative charges. That is, they may be in the form of a negative charge, or they that might arise from various sources, but the ligands are point negative charges. And the particularly in CFT, they are just the charge of the ligand is considered and not the shape and size. And in the second absorption, this theory considers only the electrostatic interaction between the metals and the ligands. So the electrostatic interaction is considered in two ways. First is the electrostatic interaction that occurs between the nucleus of the metal and the ligands. Since ligands are considered as negative point charges, so there is an interaction between the metal nucleus and the ligands. And the second electrostatic interaction that is considered is the repulsion between the electrons in the valence shell of the metal and those electrons that are present in the ligands. So these are the two basic types of electrostatic interactions that are considered in the CFT. So with these assumptions, the basic CFT proceeds further. So here, to understand the CFT, we need to consider the different types of orbitals, that is S, P, and particularly D. So we know that S orbitals, they are spherically symmetrical in nature. So any effect that is due to the because of the ligands, it is same in all the directions. So when the ligand approaches the s orbital, there is, because of the interaction, there would be an increase in total energy of the system. It is both because of the interaction of the s orbital with the ligand. So this is also, and we see an increase in energy. So, and this is also true for the filled p orbitals when we consider a transition metal ion. Now, before we go into the consider the interactions of ligands with d orbitals, we need to first look into the types of the d orbitals that are present. So first is the dxy, dxz, and dyz lobes. Now the dxy orbitals here, they are renamed as, they are named such because the lobes of this d orbital, it lie between the xy axis. Similarly, it is the dxz and dyz. The dx square minus y square, Here the lobes lie on the y axis, x and y axis, and for the dz square orbital, the lobes are present on the z axis. So in particular, we see that the d orbitals, they have been classified into two groups. So one groups that contains the dxy, xz, and yz, whose lobes they lie between the x and y axis, that is whose lobes are present between the Cartesian axis. And the second group is the dx square minus y square and dz square, whose lobes it lie along the Cartesian axis. So these are the two classification of the 5D orbitals. Now this has been shown in the classification of different d orbitals, 5D orbitals. It has been in a particularly present in a free metal atom ion. It has been shown here. Now we know, however, particularly in the transition metal atom in ion, as the ligand approaches these d orbitals, since they are 5 in number and they are different in nature, they are not equally influenced by the ligands. So these d orbitals, they in normal state they are degenerate in nature. So it degenerate means that they have the same energy. But when the ligands it approach from different directions, then the d orbitals, they are not affected equally and their degeneracy is lost. Now the interactions of these orbitals and the extent of splitting of the d orbitals, it depends on two factors. One is the nature of the ligand that approaches the metal atoms, and the distance and intensity of the force of the attraction between the central metal atom and the ligands. Now we know that since the p orbitals, they are almost fully occupied, the splitting of the p orbitals, it will not have any effect on the energy of the system. And so thus the d orbitals, they remain the most affected in presence of the ligands. And particularly if we look into f orbitals, the splitting is also the influence is very negligible, because they are well shielded, they go deep inside since they are deeply penetrating. So therefore the 4f orbitals, they are well shielded from the outer electrons, and splitting here it is observed is less. But the 5f orbitals, they give rise to a larger splitting, and we will see. So how the in octahedral fields, how this f orbital splits up and it further occupies. So there are various factors that affect the magnitude of the crystal field splitting energy. So when we look for a particular given ligand, it has been found that the delta O, here delta represents the crystal field splitting energy, and the subscript O, here it indicates a octahedral ligand field. So for a particular delta O, it does not vary much along the metal ions in the first transition series. So what happens here is this, that the crystal field splitting energy for octahedral complexes, it is for the first element, for the first transition series, is almost comparable. So when for a particular ligand, as the CFSE in octahedral complexes increases, the energy it increases with the increase in the oxidation state of the metal. Like for example, if we consider the hexa aqua complex of Fe2O, it has delta values which are less than that of the hexa aqua complex of Fe3 plus. So we see that for a particular metal atom, the higher oxidation state is present, then the crystal field splitting energy is more. Then the third point is, for a given ligand, here for a given ligand and the same stoichiometry, the magnitude of the CFSE in an octahedral complex, it increases to about 30 to 50% on passing from the 3D series to the 4D series, and again it increases by the same amount when we go from the 4D to 5D series. Like here in hexa, here in the three cases, the ligand remaining the same, whereas the central metal atom it decreases, it changes. So for cobalt, which is present in the first transition series, the CFSE corresponds to this. For the rhodium that is present in second transition series, the CFSE this, and for iridium, which is present in the third transition series, we observe a higher CFSE. So this reason might be because could be because of the higher effective nuclear charge that increases with larger distribution of the d orbitals. So also, when for a particular ligand and stereochemistry, the metal ions can be arranged according to their increase in order of CFSE, and it has been found to follow this order. So with this concept, there arises a new concept that is called as spectrochemical series. Now this series, it is an arrangement of different types of ligands that we generally employ in coordination chemistry, and these ligands, they are arranged in their increasing field strength, that is for the increasing order of their CFSE. This arrangement, the data, it came from the spectral studies, and this series is called as the spectrochemical series. Now this is quite helpful because it indicates the different spectral behavior of complexes. So here in octahedral complexes, so for example, four octahedral complexes of CO3 plus ion has been shown in table 10.1. So when we look into the complexes, the central metal atom, it remains, the central metal ion remains the same in all the four cases, but there is a difference observed in the color of the complexes. So this is explained by the spectrochemical series. In these complexes, the ligands have been changed. So the ligands at the end of the series, they have higher delta CFSE. Here, as we can see, the CFSE corresponding to cyanide ion is the highest among the all, and that is why it shows the maximum absorption and exhibits yellow color. So this is how we can explain the spectral behavior using the from the spectrochemical series. So this is also, the spectrochemical series can sometimes been useful in making certain prediction about the nature of the complex. It can also tell us, looking at the type of the ligands, we can also indicate whether a complex is a low spin complex or it is a high spin complex. So like if a particular ion, it gives a low spin complex with ammonia ligands, then it is analogous with Cn minus ions. So however, these are all purely quantitative in nature, and sometimes spectrochemical series, they have all particularly been useful for analysis of spectral feature of complexes. The three here in this figure, we have studied how the color has been, how the energy and color, they have been related. So we know that the three primary colors are red, blue and yellow, and there are also secondary colors. So in coordination complexes, as a result of the splitting of the d orbitals, so most of the energy, it always corresponds to the visible light. So since it is present in the visible region of the light of the spectrum, these complexes appeared color. So that is why most transition complexes, because of the dd transition and the energy of this transition that is lying in the visible region, so we are able to see the color. However, the colors which do not cannot be absorbed, here the colors of the solution that cannot be absorbed by light, and they appear colorless in nature. So first, coming to splitting or the CFSE in octahedral complexes. Particularly in octahedral complexes, we will consider the simplest geometry, that is ML6, where L stands for the ligand. So this complex here, it has been shown octahedral arrangement. Here it has been shown particularly when a ligand, that is six ligands, particularly in this arrangement, four ligands, they lie in one plane and the other two in a plane that is perpendicular to the first plane. So the six ligands, they lie in the corners of the regular octahedron, and when we see that these ligands, they approach the central metal atom, there is a strong force of repulsion occurring between the electrons of the ligands and that of the central metal atom. So as a result of this, the d x square and y square orbitals which lie along the axis, they are repelled more. So as a result of higher repulsion, they have higher energy. And on the other hand, the dxy, yz and zx orbitals, they will be lower than energy they will lie lower than that of the dx square minus y square and z square. So here the what we can say is, particularly for an octahedral arrangement, the splitting of the d orbitals can be, here it is shown in figure 10.4. So here in the free metal state, the 5d orbitals, they were degenerate in nature, that is they had the same energy. However, with approaching ligands, the splitting occurs and they are split into two parts. The first higher energy level, it comprises the dx square minus y square and dz square orbital, whereas the lower energy comprises of the dxy, dyz and dzx orbitals. So this separation, and here the two sets of orbitals, they have been classified called as T2G and EG, where G refers to Gerard and that, and Gerard indicates centrosymmetric, that is they are applied with a symmetric structure. So the T2G, this the d xy yz and zx, they are called as T2G orbitals, whereas dx square minus y square and dz square, they are called as the EG orbitals. Now this term delta O here, that is the crystal field splitting energy in an octahedral field, it is given as 10 dq. The here the center of this field, here it is called as the barycenter, and this corresponds the T2G level, it corresponds to minus zero point 0.4 delta O, and here this is plus zero point 0.6 delta O. The EG level, it corresponds to this. So here the each of the three T2G orbitals, it is lowered in energy of zero point 0.4 delta O. Thus each level is zero point 0.4 delta O. So total here three levels orbitals are present. The lowering in energy is zero point 0.4 into 3, that is 1.2. Similarly, the EG level, that is it is raised to an energy higher in energy of zero point 0.6 delta O. Since it contains two orbitals here, so zero point 0.6 into 2, that is 1.2 delta O. So thus the sum of these two levels, it becomes 0, and the delta O values, they usually lie in the range of 100 to 250 kilojoules per mole. So the splitting here, it is represented in the splitting of d orbitals in an octahedral field, here it is represented. Now coming to calculation of CFSE. So here in figure 10.5, the UV absorption spectrum of TiH2O6 plus, it has been shown, and here the splitting of the orbitals has been shown. Here we can see this TiH2O6 minus, it contains one unpaired electron, and that is why it first occupies the lower orbital in T2G. So and thus the calculation of electron and the electronic it is represented as T2G1 to the power 1, which indicates that it has one electron in the T2G level and EG0. So that indicates no electron is present here. However, this is present in the normal ground state. Upon excitation, this single electron, it moves to EG1. It moves from T2G to EG1, and that is why the delta 0, it transforms from T2G1 EG0 to T2G0 EG1. Because of this DD transition, here in TiOH2O whole 6 H2O6 3 plus, we see a colored complex, and we see here a, here it occupies, and we see this dd transition, and therefore we can find out the nature of transition of these complexes. So particularly here, if we consider the splitting, the nature of the ligand, it plays a very important role. So if we consider a D5 system, so here in D5 system, particularly Fe3 plus system, so two types of occupying the five different orbitals, they are possible. So here in this case, when unpaired electrons, first if we pair the five electrons, then we can find one electron remains unpaired. But however, if we place those electrons in T2G and DG, we find all the five electrons, they are remain unpaired. So this is the possible configuration, what we call it as a low spin complex, and this is for high spin complex. So particularly in a low spin complex, Hund's rule is followed, where pairing first, where the lower electron, the orbitals, they are first paired up. And in a high spin complex, here Hund's rule is not followed. Each of the orbitals, they are first singly occupied. Once all the orbitals have been singly occupied, then the pairing starts. So this is where the nature of the ligand, it plays an important role, and it determines the type of the complex, that is whether it is a high spin complex or it is a low spin complex. And here certain example has been shown. Now when we talk of the D10 configuration, so here particularly in D10 configuration, apart from D10, all other configurations, they have from D1 to D9. If we look into the EG set, then it remains completely filled. But when we talk of the D10 configuration, the EG set is completely filled. So under these circumstances, what happens is, when the EG set remains incompletely filled, the electrons from the T2, they have this possibility to jump to EG orbital, provided that the excitation energy that is supplied to the metal, it is sufficient. So because of this DD transition that happens from T2G to EG, so these compounds, they, and mostly this transition, it occurs in the visible range, and that is why they appear colored to our eyes. So when light is associated with, we know that it is delta 0 is given as h nu. So particularly in this case, the energy for TiH2O whole 6, it has been found to be, the energy for this has been found to be 20,400 centimeter inverse. Then coming to weak and strong field complexes. So to understand this, we'll start with a simple example with a D4 complex. So here there are two possibilities. So this is the splitting of the d orbital. Here the lower is the T2G level and upper is the EG level. So two types of cases are possible. The first case, where the pairing takes place provided each of the orbital, they were singly filled, and then in the T2G orbital, the pairing takes place. In the second case, all the orbitals, they are first singly filled. So as a result, in this case, we can find a concept of pairing energy. So if we look into this first case, here we see that there is the presence of one pair of, they are paired electrons, whereas when we look into the second case, we do not find any pair of electrons. So where there is a pairing of electron occurs, a certain amount of energy is associated with it, and that is called as the pairing energy. So in the first case, here the electronic, the configuration can be written as T2G4, and here the configuration is T2G3 EG1. So the total CFSE for the first case, it can be written as T2G to the power 4, that is 0 minus 0.4 delta 0 into 4, that is given by minus 1.6 delta 0 plus P, which corresponds to the pairing energy. And since one pair of electrons, paired electrons are found here, so we can write it as 1p or p. So similarly, for this case, the CFSE in the second case, it has been found to be minus 0.6 delta 0. So for the first case, where delta 0 is greater than p, then the complex has only, here the number of unpaired electrons is 2, and it is said to be in a low spin complexes. However, here it has 4 unpaired electrons, it is said to be in a high spin complexes. Now in general, it is known that strong ligands, they causes greater splitting. So as a result of greater splitting, the CFSE is high. And low spin complexes, here they are also called as strong field complexes, while high spin complexes are called as weak field complexes. So in general, what we have obtained here is, if the pairing energy is greater than the CFSC, then it is a high spin complex. If it is less than CFSC for in an octahedral field, it is a low spin complex. and it is equal to the CFSE, it indicates that both the states are in equilibrium. Now this pairing energy, it depends upon the electronic distribution of the spectra particularly, and the type of the ligand, so which finally decides the electronic configuration. It also depends on the metal ion, the ligand, and geometry of the complexes. Once we know the values of P and delta zero, we can assume we will be able to calculate the CFSE. So here in table 10.2, the pairing energy and the CFSE values in octahedral complexes for D1 they have, to D10 they have been shown here. For particularly for D1, since only one configuration is possible, it has not shown here. The for D4, here it has the pairing energy and the example of a complex, it has been shown here. Here D1 to the CFSE, particularly there is no splitting in D0. That is why it has not been shown. So in table 10.3, the CFSE for octahedral complexes, considering a weak field and a strong field, it has been found. Now let us consider the case of D5. So in a weak field, D5, it splits into T2G3 and EG2. So the number of unpaired electrons is 5, and therefore the total electron here is 0. So in a strong field, this D5, it splits as T2G to the power 5 Eg0. So therefore the number of unpaired electrons that remains is here is 1, and the CFSE, it corresponds to the 2p. Here 2p, it comes as a factor of the number of paired electrons. So this is the total energy, and this is how we can calculate the CFSE. But for that, considering the nature of the ligand in the weak field or strong field is very important. So in most of the cases, the pairing energy P, it has been ignored. So here in D6 metal, so it already contains a proper pairing. So the extra stabilization here in D6, it comes from two more paired electrons. So in practical purposes, we can ignore this pairing energy. Now coming to John Taylor distortion. So here, after octahedral and tetrahedral geometry, after, so one of the most common geometries that we encounter is square planar complexes. So we'll first consider the splitting in such complexes. So first is tetragonal distortion of octahedral geometry. This is what is called as the John Taylor distortion. So the John Taylor distortion, it gives an indication of how an octahedral geometry, it distorts into a tetragonal structure. So we know that the degeneracy of a 5d orbitals, it can be removed in the presence of a crystal field, that is in the presence of a ligand. So what happens is the removing of this degeneracy, it provides greater stability by way of CFSE. So the system is often the becomes more stable if we again remove the degeneracy. So here certain configurations, they help in this removal of the degeneracy by forming distortions. So let us, for example, we consider a high spin complex D4, and it has a distribution like T2G3 EG1. So in a regular octahedral environment, we know that the EG level, it is doubly regenerate, because the EG level, it consists of dx square minus y square and dz square orbitals. So the electrons, they can occupy either of this. So if the EG level now it splits up as a result of some consequence, then we see a distortion in the geometry of the EG level. So here, based on this, a generalized statement of this situation, it was made by John and Taylor, and it says that any nonlinear molecule in a degenerate electronic state, it will undergo distortion to remove the degeneracy and ultimately to remove the degeneracy and ultimately lowering the total energy of the system. So this theorem, it mostly tells us when a distortion is to be expected, but it cannot actually predict the magnitude of the distortion. So however, it has been seen that the undistorted system has a center of symmetry, then this will be maintained in equilibrium. So examples of John Taylor distortions, They are very common with unfilled symmetrically EG11. So these are some of the common examples where John Taylor distortions are seen. So the structure of CuH2O plus 2 in perchlorate salt, it is a classical example of John Taylor distortion. Here the CuO distances we can see particularly they are very long. Since the ion here it has a fourfold symmetry, the distortion here is referred to as tetragonal distortion. Now here in particularly in the nickel case, it has a symmetric octahedral distribution of ligands. So first let us look into this copper molecule. So in an octahedral field, when with the it is a D9 configuration, and the electronic distribution is T2G6 E3. So here two cases are possible when we will consider the case of particularly EG3. So here it is possible that dx square minus y square orbital will have one ligand, and the dz square orbital it will have two ligands. So the ligands along the x and y axis, it will be less screened from the electrostatic attraction of copper. So what happens here is this results in a tetragonal distortion of the octahedron which is along the z axis. Now in the second case, the dx square minus y square orbital, it can have two electrons, and the dz square orbital, it can have one electron. So here in this case, the two axial ligands, they are more closer to the metal ion than the other four, and here a tetragonally distorted octahedron contracted along the x-axis is observed. So these two situations, they have been shown in figure 10.8. Here we see an expansion of the x-axis, and here we see of the z-axis along the z-axis, and we see in the first case we see a contraction along the z-axis. So here delta 1 is the difference between the energy between the two EG orbitals, and here delta 2 is the difference in energy between the dxy and the other degenerate orbitals, and thus here it is shown like this. So here this clearly depicts the consequences of John Taylor distortion. So these John Taylor distortion of metal complexes which have unsymmetrical electronic distribution are mostly pronounced. So here these are the two complexes where we can some of the complexes where we can expect JT distortions. Even JT distortions are found when an octahedral complex it has 1, 2 or 5 electrons. So in general, we can say John Taylor distortions are particularly, they are more prominent in unsymmetrical electronic distortions. However, in 1, 2 and 4, they have been observed in the T2G level where the presence of unsymmetry is present. So here the John Taylor distortion it applies to excited state as well wherever we have an unsymmetrical spectrum. So this theorem it applies like particularly in this example TiH2O6 whole 3 we see the presence of one unpaired electron. So the ground state of the ion it suggested a distorted octahedral structure where the single electron it is present in the T2G, that is in the dxy orbital. Now when it goes to the excited state it is present in EG, and it is also susceptible to distortion. So there are two transitions might be accepted, that is it can move from dxy of the T2G level to the dx square minus y square in the EG level. It can also, there is a possibility that it can move from dxy of the T2G level to the higher dz square in the EG level. Now, because these two transitions are possible in the spectrum of TiH2O6 whole 3 plus, the peak that we see in the UV visible spectrum is broad in nature, and it is not because of the possibility of a single transition. It does not appear as a sharp line, it appears as a broad line. So then coming to square planar coordination complexes. So in order to understand the d orbital splitting in square planar complexes, we have to start with a octahedral compound, and then we will imagine how the square planar complex is formed by removing the octahedron. So here the in figure 10.9, the crystal field splitting of d orbitals in a tetragonally distorted field, it has been shown here. The particularly it depicts the distortion. So there are four stages that occurring that can happen during the when we consider the distortion in square planar complexes. So we start with the dxy, that is the t2g orbitals and eg orbitals of and their placement as per in splitting in octahedral complex. So as we gradually move, then we can see various types of states. We can indicate 2, 3, 4 here. So the distortion here, it follows four steps. So first is the various stages they have been depicted. So in figure 10.91, when the two transligands they are placed along the z axis, the most affected they are the is the dz square. So as a result, the dz square, it is more stable, and the dx square, x square minus y square, it gains energy and it goes to a higher level. Similarly, the other orbitals along the z axis, that is the dxz and dyz, they are also affected by this movement, and we see that the dxz and yz also comes down, and the dxy, it is remaining in its own energy position, and this is indicated in figure 10.92. So when on another ligand for the eg set of orbitals, now here if the dz square orbital, it is lowered in energy due to distortion, then the dx square minus y square, it goes up. So if one is lower, then the other has to go up. Similarly, when we look correspondingly, the energies goes up and down, and further we can see three different cases that arising in 10.93 and 4. So this is how, so combining all the figures, and if only electrostatic interactions are considered in the square planar rearrangement, then the orbital splitting parameters for a square planar complex can be overall summarized as here it is shown here. Here delta sp, it indicates the cfsc for square planar complexes. So here the splitting energy, it is from the highest dx square minus y square, followed by dxy, followed by dz square, and then dyz zx. That is, it is the summation of delta 1, delta 2, delta 3. So now looking at this figure, we can say here that this delta 1 here is equal to that of delta 0. So in general, this delta sp for square planar complexes is always higher than the cfsc of octahedral complexes. So various calculations have been made on the calculations of cfsc of delta using in square planar complexes have been made using this rule. Then coming to splitting of d orbitals in tetrahedral complexes, the tetrahedral geometry, it is very much difficult to analyze, and therefore the splitting is also very difficult to analyze. So therefore here a simplified picture has been given for the splitting of the tetrahedron, and here 10.11 shows a simple tetrahedron. So when the considering the different types of approaching of the ligands and the placement of the cubes, the final splitting of the orbitals in a tetrahedral crystal field, it is given by this. So where we can see that the eg, here we see that the two e orbitals, that is they are lower in energy, that is the dx square minus y square and dz square orbitals, they are lower in energy, and here we mark that the g has not been used here, only the e has been labeled. So since g that we used for octahedral complexes, it indicated the symmetry, but in a tetrahedral field it does not possess a center of symmetry, that is why g is not used here. Only here it is written as t2, and in the higher energy, that is t2 levels, and the lower energy, that is e levels. So now when we have an so this is the each orbital, particularly the T2 is raised here by 0 point plus 0.40, and the here E set it is lowered by minus 0.40 delta T. So by using this we can calculate the CFSE for octahedral complexes. Now there, when we compare the CFSE for octahedral and tetrahedral complexes, we have a common mathematical relation, that is the inner the tetrahedral complexes, that is delta T is equal to 4 by 9 of delta O. That is the CFSE for the tetrahedral complex is given as nearly like 4 by 9 of the CFSE of the delta O. So this is how a relation, from this relation we can see that tetrahedral complexes, they have lower CFSE as compared to those of octahedral complexes. And here in figure 10, the CFSE for D0 to D10 of high spin complexes in octahedral and tetrahedral fields, they have been shown and particular examples have been taken here. So this is how we calculate the CFSE in different fields. So then coming to applications and limitations of CFT. So we know that applications, first is coming to applications. CFT, they have been used for the calculation of lattice energy. So we know lattice energy that has been particularly useful. This from figure 11.2, we can find out the radii of ionic radius within the plot of ionic radius with increasing atomic number. From calcium to zinc, it is nearly a straight line, whereas the other points, they do not lie in the region and they have a minimum point. For table 3, when we can see, if we look into the number of the 3D 3D electrons, and we look into this plot, we can calculate the CFSE values based on the number of the d electrons. So here from this plot we can see that the D0, D5 and D10, they have 0 CFSE. So here from the shapes of the curve, the enthalpy of hydration, they can be calculated, and finally the lattice energy can be known. Then is ionic radii. So when we look into here in figure 11.2, the ionic radii, so the ionic radii can also be known from the plots. The thermodynamic and related aspects of crystal fields can also be studied. So here, for example, we consider the oxidation of CO2 to CO3, and we see the oxidation in presence of different fields of CO2 to CO3 in different fields. They have been indicated. Their standard electron volts for the reactions, that has also been indicated from 11.1 to equation 11.7. So these follow the order of the spectrochemical series, that is with increasing CFSEs. So here the oxidation in this first case, CO2 plus, that is T25 Eg2, T26 Eg1, T26 Eg0. So these is considered for like the calculation for the conversion of this process. The E0 values, they are considered, and the thermodynamics have been calculated. So the heat of ligations, or mostly the heat of the hydration. So the enthalpy of hydration of metal ions, they can be calculated. So here the in 11.3, the delta H hydration, they have been represented. Now, site preference energy. So this comprises of the spinels. The spinels have the formula Ab2O4. So where the A can be a group 2 metal or a transition metal in +2 oxidation state, and B is a group 3 metal or transition metal in the +3 oxidation state. So here in Ab2O4 unit, there are 8 tetrahedral holes and 4 octahedral holes, and the oxide ion, it forms a closed pack cubics. The normal spinels like MgAl2O4, they has 1/8 of the tetrahedral holes that are occupied by Mg, and Al3 plus, they occupy 1/2 of this. Spinels all with inverse structure, they have the inverse ions. So even intermediate cases of spinels they have been found. So here in table 11.1, values of different spinels they have been reported here, and the structure for a AB2O4 spinal is given. Now coming to the limitations of CFT. So it appears that only the electrostatic interactions have been considered here. The covalent nature has not been taken into consideration. The strength of the ligands in the spectrochemical series is not much explained. So this is also an ambiguity in the CFT. Only the metal d orbitals are considered. The ligands of the orbitals of the, like for the sp orbitals, are not at all considered. Further pi bonding has not been considered in this CFT. So molecular orbital theory, it totally takes up a different approach. It combines the concept of the metal orbitals and ligand orbitals, which hybridize together to yield new metal orbitals. So this, although MOT is molecular orbital theory, is very much, it explains more vividly, but it is very difficult to analyze using this. So hence the second, to minimize, to make it simpler, we have known as an adjusted crystal field theory, or we call it as ligand field theory. Now the crystal field theory, it has, although it has a number of limitations, but still it, the assumptions, and the assumptions made by it has been predict, it has been able to predict the energy and the geometry to some extent. Nephaloxic effect is one effect which means to support the sharing of the electrons between the ligands, and the it talks about the sharing of the electrons between the ligands and the central metal ion, that is called as the nephaloxic effect. This electron electron repulsion here in table 11.2, here the crystal field data for aqua complexes of different metal ions for the first transition series, it has been depicted here, as you can see. Then, so in table 11.3, the nephaloxitic series of ligands and metal ions, they have been presented here. Then pi bonding and molecular orbital theory. So ligands, we know they not only form sigma bonds, they also form pi bonds with the metal. So here in 11.6, the pi overlap of d orbital with various types of ligands have been shown, and this has lead to a number of like d pi, p pi, and other bonds. Here we can see metal d x square, overlap of the ligands in x square, overlap of the ligand orbitals with metal dx square and metal dxy orbitals. So as a result of this overlap, we can have a number of pi bondings such as p pi d pi, d pi d pi, d pi pi star, d pi sigma star, and other such pi bonding, they are possible here in case of metal complexes. In figure 11.8, here the pi overlap of T2 with a metal T2g orbital, it has been shown. In figure 11.9, the molecular orbital diagram for the pi system of COF6 3 minus, here it has been shown. So some of the common MO diagrams for pi system, the pi bonding, it has with ligands, it has been shown here. So with this, the applications and limitations of CFT is finished. So we'll have a class on Sunday at 11 at 11 p.m. and we'll finally finish the inorganic chemistry course on that class. So thank you for today.